All right, so what we'll do now is for you to make a start on this problem. So we'll work through this together. Okay, so difference that we've got now is we've got two forces rather than just one, but we know. So when we're calculating our moments, so we just got to add up the net moment effect of each of the forces that are acting. Okay, so we work out the moment effect of this force Ft and the moment effect of this force Nf, add them up, and that will be our net moment. So the moment effect of this force Nf should be easy enough now that we've gone through that revision of calculating moments of a force. This one may cause a little bit more trouble. So you can see I've just put a question in the chat asking whether you want me to put you in the breakout rooms to discuss the problems rather than just working on your own. So if there's a few people who do, I'm happy to just put you out in your own. And feel free to ask questions in this big group as well. Just if you're not sure about something, type in a question. I hope everyone is actually having a go at working on the problem. Don't just sit there and wait for a solution, because as you should know, you've already got the solution. So, yeah, getting there? Okay. So just do 424 to start with. Don't worry about 425. Just start with 424 and stop there. Right, so as you know, the solutions are down here. But don't look at them yet. And also, don't be afraid to paste your working up here. Okay, so I'm not sure where people are up to. Obviously, if I was in a on-campus classroom, I could walk around and have a look. But here I'm flying blind. So if you're struggling with what to do with the force Ft here, there's two approaches, right? And in my solution, I show the two different ways to deal with it. So one way to deal with it is to break this force up into components. So as we were talking about that dealing with components and how we draw components before, if we break this force up into components, the net moment of the two force components is equal to the moment of the original force itself. In the pre-tutorial videos and so on, so looking at moment of force and principle of moments. So here we've got a similar sort of problem. Let's look at the notes here. So here we've got so you've got a force at an angle, and we can find this perpendicular distance, and you can do that with this problem. Or we can make use of this Varanon's theorem, okay, which says that the moment effect of a force, the moment effect of this force, is equal to the sum of the moment effects of the components of that force. Okay, so if we break this force up into components, vertical and horizontal, and find the moments of those components, then the sum of those two will be equal to the moment of the original force times its perpendicular distance. So often what happens in structural analysis problems is that you tend to know perpendicular distances from the given dimensions of the structure that you're analysing. And often the force will be at some angle to that. Right, so here, instead of trying to work out the perpendicular distance down here, the line of action of this force is down here. Right, and then we need to work out perpendicular distance here. All right, so to do that, to find this distance here, this blue, the length of this blue line, takes a little bit of trigonometry to try and work that out, right? So usually what's easier is to work out the components of this force along directions that align with dimensions that we already know. So if we go down here, so this original problem where we've got this force at an angle, so instead of trying to work out the perpendicular distance, we know the radius of the pitch circle for the gear. And then if we work out vertical and horizontal components, we can find the net moment of those two components. Again, note the importance of where you draw the components. So this goes back to that very first quiz question that we did, where I said, what's the most accurate way to draw the components of your force? So, if you were, if you're going to draw it like that, so the horizontal component, it looks like it's offset from point 0. So you might be tempted to try and work out a distance. It may seem obvious or silly to do that, but it's showing you your component down here is kind of indicating that it's offset from point O when it isn't really. Right? Similarly, if you, instead of drawing your component over here, you draw your component like this. Right? It looks like this component now is offset further than R from point O. So that's why I say draw your components like this, so you maintain your line of action of the force. Right, so still got no numbers anywhere, no numbers, no pictures, no questions.
Sorry, Terry.
Yep.
In the wording of 425, I've just noticed it says if the resultant moment produced by A is required to be 0, determine the magnitude of FF.
Oh, it should be FT, I think.
Okay, cool. Just want to double check that one because I was like, hang on.
Yeah.
Thank you.
Anyway, that's what I assumed when I did the poll. Didn't even notice that. Thanks.
No worries.
Okay, so let's stop it. So let me know when you've got 424 done, and post the numbers that you've got in the quiz, just so I need some kind of feedback to know where people are at. Yanni's let me know that he got it wrong, but knows why he got it wrong. That's cool. If we've already done 424 one way, try and do it the other way. So, okay, thanks, Kaylin. Also, just when you be careful to not just check answers, right? Also check especially in, the way I did problems last week, and also problems next week and the following few weeks, really take note of the procedure that I use, and also look at the different, in a lot of problems I also show a couple of different ways of doing the problem. So really take note of any differences between what you've done and what I've done, and really understand whether the differences are important or not. If I've done something a certain way and you're not sure why I've done it that way, please ask. Okay, got a question. Why does the X component have 0 moment about A? Good question. I'll deal with that as we go through the solution. I would like to see more coming back from you guys, but for this question, I might, what do I do with my, there it is. Start working through a little bit. I actually changed this solution yesterday, so it's an updated version of the solution if you downloaded it previously. Solution and the solution to the next problem are one of the few where I I didn't draw something, but I decided I should really go back and draw it in. But in last week's and next week's and following, always got a proper free body diagram. In this one, you don't really need it, but anyway. So what I've done here is just to isolate the fundamentals of the problem, irrespective of what it's applied to, whether this is a foot, whether it's a part of a machine, part of a structural component of a frame, or whatever. It doesn't really matter what it is. Right? So you can take away this picture of the foot and the problem doesn't change. We've got a point here, we've got some forces, and we've got some dimensions and angles. And we're using, this is our theory that we're using, or formula that we're using to calculate our moment. Right, so we've got two forces, Ft and F, and we've got a point where we want to calculate moments about. The way I started to solve the problem was to firstly find the y component of that tendon force. You may have started with this force down here because it's a little bit easier to deal with. But I started with find the y component of the force Ft. So what I've done is to realise I can break this up into components, as I said. So there'll be a vertical component here along this line, and there'll be a horizontal component if you draw your components the way I suggest that you should. There'll be one that goes through here. And I can see that it's going to be that the moment effect of that component will be 0, but we'll deal with that a bit more in a sec. All right, so find the y component of Ft. So as soon as I'm thinking find x and y components, on my solution, I need to identify or indicate what x and y are. Right? So they could be horizontal and vertical, but they don't have to be. So as we saw in the problem last week, where we had the block with the spring sitting on a slope, it made sense for us to have our x-axis not horizontal, but aligned with the slope. Okay, and the y-axis was perpendicular to that. So in your solution, you need to indicate what x and y are and their directions. And I've also indicated there the sense of the moment that I'm taking as positive. Okay, so if I've got x and y coordinates like that, then anti-clockwise is positive for the moment. Please jump in with a question at any time, and I'll either answer it or I'll hold it off till a little bit later, like I did with Nathan's question. Okay, so drawing in my component of Ft in the y direction, so it will be along this line here. Label it Fty, and I can do, right, so I can see this little triangle here, right angle triangle. The magnitude of that component will simply be Ft cos 5, right? Because we know this angle here is 5 degrees. If we make our little triangle, right, that's our triangle in there. We can use Pythagoras to work that out. So hopefully that should be straightforward. So now to Nathan's question. Thanks, Nathan, for posting that. What about the x? And I'm sure there's other people with the same question. Right? Or there were, at the time Nathan posted the question, there were other people who had that very same question. If you can, just post yes, I did in the chat if you had the same question. Yeah, Lauren, thank you, Lauren. Anyone else? Anyone else have that same question at that time when Nathan posted the question? Yeah, awesome, great. So I've put this in here because I know that students have that question. Right? So if you have questions, please don't just rely on someone else to post the question. Please don't think you're the only person that has the question, because 9 times out of 10 or more, I reckon, there's going to be, maybe if there was a class of 6 rather than 14, there might not be someone else with the same question, but in a class of 14, there's very likely going to be at least one other person with the same question. All right, so what about the x component? So let's draw it in and see. All right, so if we draw our x component correctly, according to what I say is correctly, then, and maintaining the correct line of action of the components, then we can see that here's our component in the x direction. Its line of action passes through point A, right? So if the line of action passes through point A, the perpendicular distance between point A and the line of action is 0. Yeah, that's right, Hayoung. Yes, you're right, Hayoung. Yeah, but it's important to say, if you just write d is equal to 0, right, it doesn't tell the whole story. The whole story is that d is the perpendicular distance between the line of action of the force and the point. Right? Because there is a distance between point A and the force. Right? It's this distance here, 65. But it's that important bit of information that is often left out when we say, what's the moment of a force? Force times perpendicular distance. Okay, perpendicular distance to what? Need to have that full understanding to make sure that you get the question, that you analyse the moments correctly. All right, so now that we've established that the x component has 0 moment about A, now we can just do F times perpendicular distance. So FTY will be times 65 millimeters or 0.065, and line of action of NF is up here. So its perpendicular distance, so if we put that in, perpendicular distance from the line of from the point that we're calculating moments about to the line of the action of the force will be this blue line that I've just put in here, right, which we can see from our diagram, our information that we're given is 100. So now that we've done all our thinking, or most of our thinking, we can put these things into this equation. So I'm just giving people the opportunity to ask a question. Okay, so happy with the signs in front of the 2 moment?
Should it possibly be the other way around if T is going in the clockwise direction? Oh, no, sorry, I just saw your thing up the top. Yep.
Yep, well done, right? So the importance of, so that highlights the importance of having this in your solution, right? Without this, you don't know. So always show the details of what you're doing so that when someone else or you later on come back to look at your solution, they don't have to guess what you've done, right? If someone's got to guess, then you haven't provided enough information about what you're doing. So at your level of where you're still learning this stuff, it's sometimes a bit hard to know what information you need to put in because someone can't guess what you're doing, and the information that you can just do because it's, people should know. So here, if I left out this anti-clockwise as positive, you could say people should know that anti-clockwise is positive, but do they necessarily? Because a lot of people use clockwise as positive. Jacob, you got a question?
Yeah, so is it at the person's own discretion to decide which way is positive?
Sorry, what was the question again? Sorry.
Oh, sorry. Is it up to the person's own discretion to decide which way is positive, or is there like a tradition?
A rule? Yeah. For those who didn't hear the question, is can you just decide for yourself which is positive clockwise or anti-clockwise, or is there a rule? For 2D problems, you can choose positive clockwise or positive anti-clockwise, and it won't affect the solution. However, to be strictly correct, if you've drawn X and Y like this, so you have a positive right-hand rule X and Y coordinate set, then to be strictly correct, anti-clockwise is positive. The reason for that, who knows what the vector equation for a moment is? The vector equation for a moment is R cross F, okay? That's the correct vector equation for calculating a moment. Moment is a vector, the same as force is a vector, right? So if we have X and Y like this, and if I have a force here, say, F, so that's a vector F, and this is a vector R. What's the vector or the unit vector of the direction of this vector R? I, J, or K? All right, good, yeah. So this is I, and F is what? What's the vector direction for F? J, good. All right, so if I do I cross J, what do I get? Yeah, so I get, so R, just the R times F will give me the magnitude of the vector, but what's the vector direction if I do I cross J?
Is it in the Z direction coming out?
Yeah, but what's that in your
The
unit?
K.
K, right? right? So K, which is the Z direction. So this is X, this is Y, and this is, whoops, the Z direction, right? So our moment is actually a vector coming out of the page in the positive Z direction. Okay, and if we use the right-hand rule, so that's the direction of our moment, right? So if coming out of the page, using the right-hand rule, you should see, so you probably need to do it for yourself. I'm not sure if this is working in the mirrored video, but if you're looking at the page, right, the direction of your turning of your right hand, the thumb points in the direction of the positive axis. Right? So if we go from X to Y, the Z is pointing out this way. Right? Or if we go, for you, I'm not sure I can do that, X to Y points out that way. Yep. Make
Awesome.
sense?
Yeah, thank you.
Yep.
It's one of those things. It's like it was kind of arbitrary before, so it's easy to get confused and forget. But no, thank you for that.
Yeah, and that's why it's important to not just fall back onto the stuff that you learned previously and think, oh no, I know this, because often, you know, if I don't know, you may have done engineering studies at school or whatever, and you probably only ever dealt with moments in 2D, right? You never did this if you did engineering studies at school, you never did this, right? So you're just told use anti-clockwise as positive or use clockwise as positive, and you think, well, why? You know, what? But you know, there's usually an underlying reason that you're not told because it requires an understanding of stuff that you haven't done yet. So in high school, you don't do cross products, I don't think. You know, cross products of vectors. Right? So you can't explain to somebody why you should take anti-clockwise as positive. But now you've done maths modelling 1 and physical modelling, so now I can explain to you. All right, so now, you know, once we've done this, all right, so let's quickly look here. NF about point A is tending to rotate anti-clockwise, so that's positive, and our force Ft, I think we can see, is tending to rotate clockwise around point A, so it's negative. So that's why we've got negative here. So now we can get that. So I've got 2.09 Newton meters clockwise. Oh yeah, so the alternate way of calculating the moment of Ft. So how many people did it this way that I've been through now? Only Yanni. Right? Only Yanni's doing any work. Okay, Kaylin did it that way. Cool. All right, so the alternate method for the moment of Ft is, as I started to say, explain at the start, was to find the perpendicular distance between the line of action of Ft and point A. Anyone do it this way? Anyone use this approach? Remembering that the moment is the force times the perpendicular distance from the point we're calculating moments about to the line of action of the force. We need to know this little distance in here, right? This distance in here, D. Thanks, Jacob. All right, so in order to use this approach, we just need to use some trigonometry to work out the length of this line here, D. Right? And it's not that difficult trigonometry, so this is, should be able to work out that this is 5 degrees in here. We know the length of this line here, it's 65. So here D will be just 0.065 cos 5 degrees. You know, you should be able to see that if we put Ft times D, we're going to get the same as what we had up here. Just that the cos 5, instead of being attached to the force, is now attached to the distance. Alright, so 425 is really just an extension of the problem. So now, and this is kind of looking forward to next week when we do equilibrium problems. Really, we're saying this is an equilibrium problem using sum of the moments equals 0 as our third equilibrium equation. So last week we had particle equilibrium problems where we only had sum of the forces in the x, sum of the forces in the y direction, or sum of the vectors, vector forces equals 0. Now we're saying, okay, if this is in equilibrium in terms of moments, how do we work out the force that keeps it in equilibrium? Right? So here we've got a known NF and an unknown FT, if we change that to... So we have got the same equation here, but instead of putting in a number for 650, we just put in FT as an unknown and make it all equal to 0. So our equation now is we want the net moment to be equal to 0. Same equation. We know NF, we don't know FT. One equation, one unknown, we can solve for that. Okay? And just allow a minute or so in case someone wants to ask a question while I have a drink of water. Thanks, Yanni. All right, so now the test of whether it makes sense is to do the next problem and see if you can do it all right without looking at the solution.